Welcome back to the next video, everybody. Today's video is on extensions and deformations. So the setup is G will be a group acting on an abelian group M, and we're going to assume M is a free R module of rank N for some commutative unital ring R. So that just means M is isomorphic as modules to R to the N. Okay, and we're going to also assume that the action of G commutes with the action of R. Okay. This setup, if you've taken representation theory, should feel familiar to you. The G action then is given by just a homomorphism, a representation of G, rho from G to GLN of R. Okay, and this representation rho yields a G action on MNR, the set of N by N matrices with entries in R. And that action is given by X maps to rho of G, X rho of G inverse. This is all standard representation theory stuff. Okay, we're going to let MNR. We're going to denote that by add rho, and add 0 rho will be the submodule of trace 0 matrices. So all the matrices here with trace 0. Okay, an extension of M is just a short exact sequence 0 to M to E to M to 0, where E here is an RG module, and alpha and beta, these maps here, are just RG module homomorphisms. What is RG? It's called the group ring of G over R, which formally is the set of maps F from G to R of finite support. But one way that one of my colleagues helped me to think about RG modules in general is just they're to be thought of as G modules equipped with a compatible R action, essentially. Okay, so what is an equivalence of extensions? It's given by the obvious commutative diagram. So let's say I wanted to say that E was equivalent to E prime as extensions of M. What I would mean by that is there would be another, I'd take both of my short exact sequences here. Okay, and I would equip this pair of exact sequences of extensions, if you like, with RG module isomorphisms from E to E prime, and then equalities from M to M as my outer connecting maps. That's what an equivalence of extensions of M is. Let's denote by X1 of MM the set of equivalence classes of extensions of M. Because in reality, what's going on here is you could call this an extension of M by M, actually. E is an extension of M by M. Okay, so that's what this notation is trying to get across. Okay, so now let's apparently shift gears and let's talk about infinitesimal deformations. So let's let R adjoin epsilon denote the ring R adjoin T mod the ideal generated by T squared, so that effectively we're attacking on this little guy epsilon here whose square is 0. An infinitesimal deformation of rho, so this rho that I have up here from G to GLN of R, okay, is an extension of rho to another representation, let's call it rho prime from G to GLN of R adjoin epsilon, such that rho prime maps to rho under the map epsilon maps to 0. So in other words, we have this commuting triangle, rho here, rho prime here. Okay, and then under the map epsilon goes to 0, we have a commuting triangle. Okay, and we're going to say two such deformations, rho prime and rho double prime, are equivalent. There's a matrix A which is equivalent to the identity mod epsilon, such that rho prime and rho double prime are conjugate to each other by A. Okay, this is, if you go way back to my earliest videos in my series of lectures on Fermat's theorem, we talked about equivalence of deformations a while ago. This is just equivalence of infinitesimal deformations. Okay, so a quick example here. Let's let R be a local ring with maximal ideal M. And let's suppose that we have extended rho to rho tilde from G to GLN of R adjoin T, or if R is complete, to GLN of R, like double adjoin T, so the formal power series ring in T with coefficients in R. Then we can evaluate T at elements of M, and that'll just give us a representation congruent to rho mod M. So that's one way that the theory of infinitesimal deformations kind of shows up frequently, especially when we're discussing Fermat's theorem and modularity and things like that. Okay, crucial proposition. This probably should be called a theorem, actually, but let's let G be a group acting on a free finite rank R module M, such that the action of G commutes with the action of R. So same as the setup above. Then the following three sets are in bijective correspondence. So we have the first cohomology group, H1 of G add rho. Then we have the set of extensions of M by M, x1 of MM. And then we have the set of equivalence classes of infinitesimal deformations of rho. Okay, so this is crucial for us. So for a proof, see CSS page 109. So what we want to do in the proof of modularity is to consider deformations with additional imposed restrictions, as we've briefly talked about in the past. But what you see by the above proposition is that this is the same as considering cohomology classes lying in certain special subsets of H1 of G add rho. Okay. So for example, let's suppose I want to look at deformations where the determinant remains unchanged. In other words, I want to compare det rho to det of 1 plus epsilon C rho for some matrix C. Okay. Well, if you use a well-known formula for the determinant of the sum of two 2x2 matrices and the fact that epsilon squared is 0, you can calculate as an easy exercise that det of I plus epsilon C rho is nothing but 1 plus epsilon trace of C det rho. Okay, well, if I'm considering deformations where the determinant remains unchanged, this is then equivalent to imposing the condition on my deformation that C is an add 0 rho, right? When will these two guys be the same? If and only if trace of C is 0, right? So the determinant being unchanged by infinitesimal deformation is the same as requiring that C is a trace 0 matrix. Now, since add rho is add 0 rho direct sum R, where R is the scalar matrices equipped with the trivial G action, then we have H1 of G add rho is H1 of G add 0 rho direct sum H1 of GR. Because it turns out cohomology respects direct sums. You can find a proof of that, for example, in Milne's class field theory notes. And it's this first component here that gives us the classes of infinitesimal deformations with fixed determinant. That's what's going on here. Okay. Okay, so that's just kind of one example of how you can powerfully use that proposition above. So we'll end with a quick example here. Let's let P be a prime, and we'll take a cohomology class C in H1, an unramified class, basically. So it's a C and H1 of GP mod IP add rho to IP, the kernel of the restriction map H1 GP add rho to H1 of IP add rho. And we'll let rho prime be the corresponding deformation, which exists by the proposition. Okay. Then what happens is rho prime restricted to inertia at P is equivalent to the trivial deformation. That's kind of what's going on here. What I mean is rho prime restricted to IP is the same as rho restricted to IP. And so what's going on here is rho prime is unramified at P if and only if rho is unramified at P. Okay, that is if and only if rho restricted to IP is trivial if you don't remember what it means for a representation to be unramified at a prime. And moreover, any ramification of rho prime actually is admitted or comes from ramification of rho. Basically, unramified classes are extremely well named because they translate to not only unramified deformations, but deformations whose ramification comes from ramification in the smaller and the lower representation rho. Okay, and so we will move on next time, and we will talk about a little bit about generalized Selmer groups in the next video. So I think that'll be on Sunday, and so I'll see you then, and thanks for watching.